Hello, good morning, everyone. Yeah, let's start the tutorial today. So today we are going to look at the eh it's not correct. Okay, so this is the one. Okay, so today we will look at homework 5, and then we will talk about 5 questions from it. All of them are very easy, so I hope that this tutorial will end very quickly. So the first one is a little bit challenging. So here, in this question, we want to show that the cardinality of the real number set is the same as the cardinality of the positive real number set. So how can we show this is true? Okay, for this one, we can show this by construction. And if you want to challenge yourself, then you can actually skip this tutorial first and think about the problem first. Okay. What I'm going to give you a solution here is we are going to design a one-to-one correspondence F that maps from this real number set to the positive real number set. And the correspondence F that we have here will have this property. So all the numbers from minus infinity to 0 inclusively, including 0, will be mapped to 0 and 1 to this range. And then all the numbers from 0 to infinity will be mapped to 1 up to infinity. So basically, we are trying to do what? We are trying to map this one to this one, the next one to the next one, and 0 to 1. And similarly, for this one, we are going to map it to here. Okay? So let's see how we can do so. So remember, if you want to challenge yourself, then make a pause here, or skip this tutorial completely. Okay, this is an example solution. So the function f that we have here is this one. So let's talk about the latter part. So this latter part handles the case where the value of x is strictly greater than 0, so from 0 to infinity. So how can we do so? So simply we map x to x plus 1. So we will see that there is a one-to-one correspondence between any number here and any number here. So if you get a number x here, you can obviously get a number x here, or x plus 1 here, that is inside here. Similarly, if you have a number, let's say y here, then y minus 1 will be in this range, so we can go back. And for the other part, it is also like this. So what I want here is I want to have 0 mapped to 1. So how can I do so? So I just make 0 into 1 and divide it by 1. So in essentially, what we are going to do here is we are going to add 1 to each of the numbers here. Sorry, I should say we are going to use 1 minus each of the number here, so that after doing so, we will get the number between 1 to infinity. And then after that, we take the inverse of it, divided by 1. Then in that case, we will have this as a result. So you can check it by yourself that it is indeed a one-to-one correspondence. Now, if it is not, then please tell me. So I may be making mistakes. So hopefully this is a one-to-one correspondence. And if we have a one-to-one correspondence, what does that mean? It means that the cardinality of this set is the same as the cardinality of this set. And we are done. Okay? So question 8 is an example like this. So we let x to be the set such that, first of all, it contains all the real numbers between 0 and 1 such that the particular real number will have k decimal places, and k is some number in the natural number set. Okay, so obviously we will see that x is a subset of the rational numbers. It is because for each of the number x that we are selecting here, for instance, let's say the x that we have here is 0.123. In that case, the number has exactly 3 decimal places, right? 0.123, then in that case, the number can be expressed as 123 divided by 1000. So it is a ratio between two integers. In such a case, it is a rational number. So all the numbers of x here that we are selecting, they are rational numbers. Because rational number set is a countable set, so in that case, this big X set is a subset of a countable set, so it must be countable. But somehow, someone tries to prove that X is uncountable using the diagonal method. So yeah, I'm not going to explain this. So if you have a chance, yeah, read this carefully. So this proof really copies that from the diagonal proof that the real number set is uncountable. So we are proving real number sets restricted to the case of 0 and 1 will be uncountable. So it is very similar to that one. But somehow we know that X is a countable set. So this proof must be wrong. So what's wrong with this proof? So again, if you have not worked on this problem already, yeah, please spend some time and see if you can discover the mistake. So in order to show that this is a wrong proof, it is not like you are giving a proof that X is countable. So it doesn't help to pick out the mistake in the proof. So we want to do the debugging. So there must be some bug, some problems, some mistake inside this proof. We want to find it out. So in particular, this is something wrong. So this diagonal proof tries to construct some number x and claims that this x is not able to be included in the set. So we have a contradiction. But the actual contradiction doesn't occur. It is because the constructed number does not fall into the set original set big X. So it is very natural that we can have a constructed number that does not appear in the listing that we have. Yeah. So basically, this proof is to show by contradiction, so that we claim that every number in the big set X can be listed without any problem, and the construction constructs a number that cannot be listed and claims that this is a contradiction. But it's nothing wrong, because the number that is constructed was not originally in the big set X. So it is natural that it will not be listed. So it is not required it to be listed. So there is no contradiction at all. Yeah, so spend some time to understand this proof. This will help you to make sure that you understand why the original diagonal proof works for real numbers, but then it doesn't work for the special case here. Okay, and then we have another question. So we want to find three sets W, X, Y, such that W is an element of X, X is an element of Y, and W is not an element of Y. Now notice that this question is actually super simple. It just wants to make sure, that you understand the difference between the notation element and the notation subset. Now, if this is changed to subset, so if I know that W is a subset of X, X is a subset of Y, then we must have W is a subset of Y. But for element, it's not true. So for instance, we can have a super simple example. W is just a set containing the integer 1. X is a set that contains a set which contains the integer 1. So we will see that W is a subset of X. Is that okay? And Y is a subset. Y is a set that contains a set that contains a set of 1. So we will see that you can find X as an element of Y. But obviously, Y has only one item, which is a set of a set, and then it is not equal to W. W is just a set. So W is not an element of Y. Yeah, you can also make an even simpler example. So you can actually take away the 1 here. So we can start by having W is an empty set, X is a set containing an empty set, and Y is a set containing a set that contains an empty set. Okay, so you can construct an example for this question very easily. So this question is nothing special, just to clarify the difference between subset and element. Okay, the next question is a counting problem. So we have this information. We know that a quarter of the 5 element subsets of 1, 2, 3, 4, 5, 6 up to n contains 7. So we want to find out what is the value of n. So among all the 5 element subsets, so how many of them? So there are going to be n choose 5. N choose 5 of them. We know that 1/4 of all these subsets will contain 7 as an element. So how many 5 element subset contains 7? So we can ask ourselves this question first. So in order to get a 5 element subset that contains 7, then 7 must be an element that we want to choose, but then we need to select 4 more items from the remaining n-1 item in order to construct a 5 element set with 7 inside. So the number of 5 element sets containing 7 can be counted as n-1 choose 4. So we know the quantity of these two terms, then immediately, this is from a description, we will have n-1 choose 4. When it is divided by n choose 5, it is equal to 1/4. So after some simplification or calculation, so this is actually very easy to compute. This is n-1 to the power 4 falling, 4 to the power 4 falling. This is n to the power 5 falling, 5 to the power 5 falling. So in such a case, we will see that n-1 to the power 4 falling cancels with a lot of terms of n to the power 5 falling, right? So we have only n left here. This is 5 to the power 5 falling, 4 to the power 4 falling. So we have a 5 left here. So in the end, we will have 5 divided by n is equal to 4. So after doing some simplification, we should get n to be 20. I hope this is correct. Okay. And finally, we have question 13. Now, question 13, we are given a function g. G has domain integer set as the domain, and also the integer set as a codomain. And the function of g maps the integer n into n divided by 2, taking the floor. So when n is equal to 2, we get g of n is equal to 1. When n is equal to 5, we get n is equal to 2. Is that okay? So when n is equal to -1, we should get this one also to be -1. Okay? So the floor function is the closest integer that is not exceeding the value. So if n is equal to, let's say, -1, then -1 divided by 2 will be -0.5, and the closest integer not greater than this -0.5 will be -1. So g -1 will be -1. G -2 will also be -1. Okay? And the question here asks us whether g is a surjection and whether g is a bijection. Now, the purpose of this proof of this problem is we want to make sure that you understand how to formally show a function is a surjection or not, and how to show a function is a bijection or not. So it is not just ask you whether it is a yes or no, but you need to explain why it is true. So first of all, so this is the function g. Now we want to ask whether g is a surjection. So we need to understand the meaning of surjection before we can answer this question. So surjection means that every item in the codomain is being mapped. Okay, is being mapped by some item from the domain. So in order to show that this is a surjection, it is really yes, we want to make sure that every x in the codomain yeah, it is really mapped by someone. So it turns out that we give a construction, we show that, yeah, by setting n to be 2 times x, so for every integer x, we must have 2x is an integer. So 2x appears in the domain, and then g of 2x, it turns out that it is equal to x. So what does that mean? So there must always be some item from the domain. After mapping by g, we get it to be equal to x. So g2x is equal to x gives us an evidence that the function g is a surjection. Now, it turns out that G is not a bijection. So if it is not a bijection, then there must be something wrong. Either it is not an injection or it is not a surjection. Now, in this example, we know that G is already a surjection. So you just need to show that G is not an injection, then we can say it is no. So in particular, to show that it is not an injection, we can give a counter example. So we find that G of 0 and G of 1 will both map the value 0 and 1 to the value of 0. So G0 and G1 is equal to 0. So in that case, it is not 1 to 1. It is now 2, at least 2 to 1, or many to 1. So if this is the case, then it is not injection, and it is not an injection, then it is not a bijection. Okay, so in your exercise or in your exam, you need to give reasons, yeah, to show why something is true, why it is an injection, why it is a surjection, why it is not an injection, why it is not a surjection. Okay, so that's all for today's tutorial. Yeah, so I think all the questions here are pretty much easy. So let's see if you, excuse me, let's see if you have any problem that you want to ask me here. Okay, okay, so let me check the web page. Oh, question 7. Yeah. Oh, yeah, thanks a lot. Question 7, yes. Excellent. So we can have a very simple function. We can map, yes, design the function fx such that fx is equal to e to the power x or 2 to the power x. Yeah, that's a very, very, very simple solution. Thanks so much. And then, yeah, our tutors are still busy in marking the exam. Hopefully, it should be ready in 1 week. So please give them around 2 weeks to mark the exam. Yeah. Okay. So thanks a lot. And then, yeah. So thank you. And then see you again on Wednesday. So on Wednesday, we will continue to talk about uh, graphs. And then, yeah, we will talk about something that is exciting and interesting. Yeah, thanks all for coming. Okay, I'll end. Yeah, I'll end the stream now. Thanks. Thank you.